From Unit 5.1 to 5.7, we learn all different properties and operations of polynomial functions. In this unit, we're going to learn how to apply all these polynomial functions in the real-world situations. When we talk about applying polynomial models in the real world, we're basically talking about how to fit data to linear, quadratic, cubic, or quadratic models. A linear model is a function which has a power of 1, and quadratic, we're talking about function have a power of 2, and cubic is a function, this time I write f of x is equal to, say, x cubic plus 1, and the quadratic model is a function which has the biggest power of 4, so that's something something. And the data here means a relationship between x and y, where x is the input and the y is the output. Or sometimes we call it independent variable and dependent variable. First, let's talk about what n plus 1 point principle is. N represents the power of the function. Basically means if you have a function, say f of x equal to x plus 1, the n right here is 1, so we need 1 plus 1 points to control or determine the line. In other words, if you have function, say this time is x squared plus x plus 2, the biggest power here is the n, which equal to 2, so we need 2 plus 1 points to determine this parabola. So we need 3 points to determine the parabola. In other words, if you're asked to, say, construct the graph of this linear function where n equal to 1, then you need 2 points to graph of this linear function. And when you're asked to construct a graph for this function where n equal to 2, you need 3 points, and so on and so forth. Now let me give you an example. If you're given a set of data and you're asked to construct a model to fit all these data, we call these regression models. As we learned before, x is the input and y is the output. Now you're given 5 data where x equal to 0, 5, 10, 15, and 20, and y equal to all these values. You can use your graphing calculator to come up with different models to fit this data. Just for teaching purpose, right now I just show you 3. They're either the linear model like this, or quadratic models like this, or the last one is the cubic model. Then you may ask, should I use the linear model, the straight line, to fit all these data? Or should I use quadratic model to fit these data? Or should I use the cubic model to fit all these data? It all depends on the context, on the questions. What I'm trying to tell you here, when you're given a set of data, you can use different models to fit all these data. The most important part is which one you're going to apply. And in the example number 3, you're going to find out which one would make more sense in the real world context. And there is no one definite answer. Now let's start with a mathematical model first before we apply the concept in a real-world context. Here's the question. It asks you, what polynomial function will have a graph that has these 4 points passing through it? So according to the n+1 point principle, we know the function that has these 4 points are a cubic function, because in the cubic function the biggest power is 3, and go back to the n+1 principle. That means the 4 points will control or determine the graph. Since there are 4 points given, so we know there will be one particular or unique cubic polynomial function that will fit all these points perfectly. The graph is going to be something like this, and the 4 points here will be on this graph. Since these 4 points passing through the graph, so we know when we put it back to this standard form, it will make this equation come true. So we substitute, for example, the first one, the x value, which is a to the x right here, and -3 is the y right here. So we do the same thing for the 4 points. We got 4 different equations. Once we know these 4 equations, we can solve for the variables of a, b, c, and d by using matrix. I'm going to show you in the next slide now. Now we can use the matrix form in your calculator to figure out the value of these 4 coefficients a, b, c, and d. After you make use of the RREF function, then you know the value of a, b, c, and d is going to be like this. We plug the coefficients back into the original function, and this is the cubic function where all the 4 points will passing through here. And you can always use the cubic reg, which is cubic regressions function, in your graphing calculator to check if these 4 points are actually lying on the graph. I'm going to show these in a separate videos of how to use the calculator to do this. Here's a real-world example to give you a set of data regarding how much milk Wisconsin dairy farms produce in these 3 years. And to plug in the data given here into the calculator. In this case, the L1, which is the X, is the year, and the blue numbers here is how many of the milk production is. So it is Y, and in your calculator it's going to be L2, which is equal to the milk production of all these dairy farms. But look at that, when they plug in the data for X, they take away the year right here. So they use a number to quantify the year instead of put down the actual number of the year. So 55 stand for 1955 and 80 stand for 1980, while 105 represent 2005. So once you plug in all this data, because they ask you the linear models, so they give you the hints that we're going to use linear model. Could you use quadratic or could you use cubic? We're going to talk about it in the next problem. But right now, since the question asking you to use the linear model, so we use the linear regression right here. After you plug in all this value, you generate all this data, then you have this linear regression line. Once we have this linear function generated by the linear regression model, we can use it to estimate the milk production in year 2000. Since when we input the data, we input the data of 2005 as 105, so the year 2000 is going to be right here, which is 100, because it's 5 years before 2005. This one is representing 2005. So we're going to plug in 100 here to estimate the milk production in year 2000. In the last example, we are given 3 data, and the question asks us to use a linear model to model the whole situation. But you may ask, could I use a quadratic model to do that? The answer is yes. Since we have 3 points, we can actually graph a quadratic model which will pass through these 3 points. The question is, which one should I use to model the dairy farm's production? Linear or quadratic? The linear model would be more appropriate in this case because we understand the milk production in a normal situation will rise continuously as years goes by. In the linear model, they have a line like this, so it represents as year goes by. This is the year, this is the milk production. We would think the milk production will continue to rise as the years increase. But when you look at the quadratic model, they're talking about in a particular year, after this is the maximum point, the milk production will start to decrease. Would that happen? It might, but it looks like in the real world context, the linear model is more appropriate to apply in this situation. So we cannot say for sure which model we're going to apply. We have to base on our common sense to analyze the situation differently and then apply different models in different situations.